All right, this first page, since it's been a little while, I'll just briefly go through it. This is talking about electric forces, and electrostatics really just means we're not into current yet. Current is when things are going to flow. We're going to have charges flowing through wires, and we'll talk about voltage and amperage and stuff like that. But in this, we're mostly just talking about charges kind of getting where they need to go and sitting there, and every once in a while shocking somebody. So are you looking for the old one or the new one? The new one, okay. So like charges repel, unlike charges attract, electrons are negative, protons are positive, and an important point on the back here is protons can't flow. So in conductors, electrons are moving through them. In insulators, nothing's moving through, but in conductors, it's just the electrons, it's not the protons. Now, I'm going to show you, I'm going to try to control myself and talk about these diagrams in a way that doesn't show my bias, which is that they really annoy me. I'm going to see if I could not let that come out before we get to number 5, and then I can just release all my venom at that point. So let's see. Now, if you want to, if you're just really, what's the word? I don't know. Boiling over, and you want to complain about the diagrams, feel free to do that. And then I'll join you, but not until, I won't join you until you do it. So what this is showing, well, let's just write this first. The two figures below. This is really below, and this is sort of to the side, below-ish. They're examples of charging by induction. Mr. Pennington used to just write induction here, I think, or maybe he had a bigger space. But I want to write charging by induction because I think induction can mean different things. Does anybody have an induction stove in your kitchen? You do? I really lobbied for one. We got our kitchen redone, and I wanted one because I wanted to do all electric stuff. But my wife wanted a really big one, and they didn't have one the right size. Anyway, induction stoves have basically a changing magnetic field in the stove that causes current to flow through your pots. And that current causes heating, resistance heating. So it's just like, without even directly touching your pots, they could be levitated above your stove without heating anything else around. You could be sitting on the stove, next to it. It wouldn't do anything to you, but it would cause current to flow in that pot, and it would heat it up. So that's one kind of induction. You need one of these? Let's see. Are they expensive? These papers? I'm going to print some more. They're kind of expensive, but I'll print some. No, they're not very expensive. In fact, if you want just a little hot plate to do some cooking in a dorm room or something, you can get a portable one. You can just set on a table. Yeah, but in a full-scale size stovetop. How do they compare to traditional? Probably more expensive. Sorry, I've lost my place. I can't talk and scroll. How many people need? Raise your hand if you need a copy of this original one. Nobody? Okay, one? No. I'll do 3. There's one for Cam, one for Evan, and one for Alex, and then one for the other person who's not reminding me. See what I printed too? I'm pretty okay. We're good. All right. So this is a different thing. Charging by induction in this case just means charging something using a charged object to charge another object without touching. So it's kind of like the induction stove thing, but it's inducing a charge. It's not inducing current like with your cook stove. Yeah. So here's what happens. You rub an acrylic rod against a rabbit, and the acrylic rod, no, sorry, that's kind of backward. Silk? I don't know. Anyway, you rub this rod against something that really likes electrons, and its electrons get taken by the other thing, and then the rod is positive. And then you hold the rod next to this object right here. Can you guess if this is a conductor or an insulator? What do you think it's supposed to be based on the way it's drawn? So if the negatives have moved all the way to this side and the positives have moved all the way to the other side, what kind of thing does that happen in? Conductors. And I think it says, it doesn't say it up here. It doesn't say this is a conductor, but I'm just going to label it. This is a conductor. This rod here, it could be a conductor. It doesn't have to be a conductor. It's probably best if it's an insulator, because once you get it charged, you can touch it. And if it's an insulator, it'll keep its charge. It's not like its charge can flow into you or out of you. So, does it make sense that this left side of the conductor becomes negative and the right side becomes positive? What they don't show is what it looked like before, which is probably like this. This is the before it's been messed with state. And then you bring in a positive thing next to it, and that pulls the negative charge to the left side and repels the positive charge to the right side. Make sense? Okay. So that's step one. If you want to, the whole point is to charge this thing, and by the end it's charged. There are two things that I can't, never mind. So you bring the positive thing in, it pulls the negative charges to the left, repels the positive charges to the right. Then you touch a ground wire to this. So we'll talk about what the ground is later, but basically the ground is a place with, it's either a source or a sink for charge or electrons. So it can give up electrons and it can take electrons. In this case, what's happening? Is the ground giving up electrons or taking electrons? No, it's giving them. So this electron is going this way, and the number of positives here has decreased from 3 to 2. So if you figured out the net charge of this, it would be 0. What would the net charge of this be? -2, because we've got 3 negatives, 1 positive, net charge -2. And it's because two electrons must have jumped onto it and then canceled out a couple of these protons. So the ground is disconnected. The ground could be a person. It could be me touching this insulator, or sorry, this conductor, and giving it electrons. And then the ground is disconnected, and it stays like it is. And then the rod is taken away, and now the whole thing's negative. So it started out neutral, and now it's negative because some negative charges came from the ground. The first thing I don't like about it is, what would the net charge of this be, the way it's drawn? -4. So I'm just going to erase that. I say erase. I'm crossing it out. And I'm just going to put 1 positive there because this makes more sense to me. So for 2 reasons. If you have 3 negatives here and you have 1 positive and you just move this thing away, you're still going to have 3 negatives and 1 positive. And what they're probably going to do is the negatives are going to repel one another and try to move away from one another. And the positive is going to be attracted to the negatives, and they're going to reach some kind of equilibrium, maybe like this, where they're evenly distributed. Here with the rod, that pulls the negatives over here and pushes the positives to the right. Okay, I can't stand this anymore. Does anybody know what's annoying about this? This is so wrong in a lot of ways. Yeah. The negative charge coming out of the ground, that's okay. That's all right. The what? Existing? No, you can have pluses. They're okay. But you're on the right track. What kind of charges actually move in a conductor? Negatives. So this makes it look like it pulls the negatives over this way and it pushes the positives over that way. In an atom, where are the positive charges? In the nucleus. It's not, if you moved a bunch of nuclei over here, this thing will get heavy on this side. That makes no sense. You can't have positive charges flow through a conductor. Only negative charges can flow. So what they're trying to show is the left side does get negative and the right side gets positive, but it doesn't happen this way. So what I want to do, I'm going to take this diagram, but do it in a way that to me makes more sense. So I'm going to redraw this here, and then I'm going to redraw this next one right here. I guess, wait, this next one right here next to that. So we start out with two neutral conducting spheres touching one another. I'm going to put two protons right here. How many electrons should I have in that conductor? 2. And I'll put them right there. And then over here I'll do the same thing, except I'm going to do it like this. Why didn't I put the positive on top? It just looks funny right here, having two negatives right next to one another. They wouldn't like that. So this is all okay. I'm comfortable with this. This has a 0 charge. This has a 0 charge. So if you bring this thing in and you put it right over here, positive wand right here. I'm not going to draw it in because it's not here yet. But what's it going to cause movement of? The positives or the negatives? The negatives. So all the negatives are going to get drawn over there. What's going to happen to the positives? Nothing. Nothing happens to the positives. Maybe. I mean, there might be a little bit of force, but it would be like the wand itself would push this whole sphere over a little bit, but they're locked in place there. And I've simplified it because there should be billions of atoms in here with billions of protons, and they would be all evenly distributed. But the proton that's here and the proton that's here and the proton that's here, they're just stuck there. They can't go anywhere unless you actually rip out a chunk of metal and move it to the other side. So those stay where they are, and all four of the do you think all, don't do this because this is wrong. Why would all four of the electrons not do that? They don't like one another. They like this, but they don't like one another, so it's kind of a compromise. I don't know. They're definitely going to shift over to the left. Exactly where they would go, I don't really know. I'm just going to draw it like this, which I feel okay with because they would get pulled to this side. They can move through the conductors. They're not going to be really close to one another, though, because they don't like one another. One flaw with this, these are just the excess charges. I mean, there are millions more electrons and there are millions more protons, but you can't draw them all. So we're just drawing a few as representative. So anyway, at this point, what's the charge of the sphere on the left? -2, and the charge of that's +2, so these have been charged by induction. So they're just simplifying things here. The way they're showing it is two neutral spheres. You hold a positive rod on the left side. Negative charge goes to the left. Positive charge goes to the right. That doesn't really happen because positive charges can't move. So tell me again, why does this become positive if positive charges can't move? This area really would become positive. Why? Because the negative's left. And so it's got an excess of protons over electrons. So in the next step, you disconnect these two spheres. And then in the final step, you take the wand away. And then you've got two charged spheres. So I did this before, but not everybody was here. And I think it's worth doing again. So let me just do this charging by induction, hopefully successfully. I have this little, these are insulating stands with a conductor. And here's another conductor. And I'm going to put them in there so they're touching one another. And plug in my sniffer. Or it's an electric field detector, but I like to call it the sniffer. And right now it's thinking something's positive. It's sniffing positive charge. So let's go. I don't know whether to go with high sensitivity. I'll try high sensitivity and sniff, 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 sniff. There's no charge there. So do you remember when I rubbed these two things? Uh-oh. There's some charge on this already. That's okay. I'm just going to make it worse. So when I rub the wool against the styrofoam, the wool has less of an affinity for electrons. So the styrofoam is really negative, the wool is positive because the electrons went to the styrofoam. All right, let me reset this, pull it out. Ah, dang. Reset it, reset it. Okay, now I'm bringing this in. And what I'm trying to do without actually touching this thing is I'm trying to use the negativeness of this to chase all the electrons to the other end of this connected metal piece. So there should be more electrons over there now. Now if I separate it, they shouldn't be able to get back. Huh. And, oh, sorry. Well, I think I'm interfering with the field, so let me do it again. Reset. Maybe I should go to, let's try low sensitivity. Stuff that tells me at low sensitivity, nothing's going to happen at all. All right. What the world? Okay. Well, back to high sensitivity. Okay, so red, blue. Red, blue. And what I wanted to do, let me touch this one. The red goes down. The blue. Yeah, so there's just some issue with baseline. Like, anyway. So you saw it. The metal plate, there's a ground wire on here. I'm not really sure why it helps to connect this thing to the metal plate. Supposedly these demonstrations just work better on the metal plate. I don't know why. I'd have to think about it. Maybe I could come up with some explanation if I did. Should I try it just on the table and see if it still works? Get rid of that plate. Maybe it's just so they could make extra money. There's absolutely no reason for the plate. Might even make things worse. I think there needs to be a medium sensitivity. So it wasn't like we could buy it without the plate. It just comes with it. So, all right. Now we're on to the next page. Oh wait, no. What's fishy and misleading about the diagrams above? Protons can't move. Positive charge doesn't flow through, like, I'm just going to say protons don't flow through conductors. Right, so you can have, in a solution, you can have ions flowing through, and they could be positive ions or negative ions. Just floating around. Yeah. And they can move. Yeah. All right, so now to this. And we won't get very far. We're going to be done soon. And a nice way to unwind at the end of the day might be to have John Travolta shock himself. It's part of your homework assignment. So this is a very long-winded discussion of ground. And we'll be talking about the ground again and again. Many times, literally, the ground is the ground. But it could be a lot of different things. It could be a person. It could be a table. It could be plumbing. It could be some large object. Usually is what we refer to as the ground. Yeah. Yeah. And well, so let me read this and then I'll try to explain. It's kind of a weird concept. So it's usually a large, nearly neutral reservoir of charge. And the Earth is an example of a ground into which excess charge can flow from higher concentration to lower concentration. So if you've done chemistry and we talked about concentration gradients, it's kind of like that. Things want to equilibrate, and the ground is a source or a sink that things can flow from or to. In reality, the ground usually serves, oh, come on, focus. Once in a while, my camera stops focusing. Focus. I used to play Ultimate a long time ago with this Cajun guy, and he used to, when he was playing defense, he would say, "Come on, Lucian! Come on, Lucian! Come on, Lucian!" His name was Lucian Junkin, and I didn't realize he was talking to himself. I thought, who is Lucian? So that was how he would motivate himself. Cajun? Like the seasoning. And so he lived in, yes. This was in Houston, Texas. That's where I went to school. And he was from Louisiana. That's where the Cajuns are. Sort of like that's where the seasoning comes from too. Yeah. Kind of a French, people of French origin, sort of French speaking. They have the Creole. I don't know. I'm not going to get into it. Yeah. So, moving on. I wish this thing would focus again. Not me, but it needs to focus. It's important that the ground is a large enough reservoir of charged particles, so that adding or subtracting electrons does not significantly change its overall charge concentration. All right, I'm going to stop reading that. Here, let me talk about John for voltage a little bit. You're going to see this. So John charges himself up, or you charge John up. And then John's got this swivelly arm, and there's a doorknob over here. And John touches the doorknob, and guess what happens? Sometimes he says, "Kazouch," and sometimes he says, "Zouch," but every time there's a big lightning bolt that goes out of his arm. So if I charge myself up, I've got a bunch of negative charge, and this thing is neutral, and I touch it, I've got a high concentration of negative charge, it's neutral, so it can kind of flow out of me. The electrons want to get away from one another, and this gives them a place to go. The problem is, this is a pretty little, yeah, I guess that's what I meant to say. It's a fairly small tape measure. So if I keep charging myself, and it's a pretty little tape measure, if I do say so. So if I keep charging myself up, and I keep shocking this thing, and I keep sending more and more electrons into it, am I going to be able to do that forever? Because eventually what's going to happen to this, it's going to be negative as I am, and then when I touch it, it's not an escape route at all for my electrons anymore. So for something to be a good ground, it needs to be really big, like the Earth. So the Earth is just about neutral. If this were the size of the Earth, and I were negatively charged and I touched it, my excess electrons could push away from one another and they could flow out into the Earth. And then once they got in the Earth, they could spread out into the Earth. And overall, that's not going to change in the location right here at the surface. It's not going to change the charge of the Earth. And it's sort of a concentration thing. Same would go for positives. If I were positively charged and I touch this, I might get a shock. But if I kept positively charging myself and touching this and touching this and touching this, I would take enough electrons out of it that eventually it would have a positive charge too. And then if I'm positive and it's positive, I can't pull any more electrons out of it. I can no longer use it to neutralize myself. Darren? You'd see a little lightning bolt, and you'd feel a zouch, or maybe a kazouch in some circumstances. So the concept of ground is going to come up again and again. It's just it's what I said it was, and we'll talk about it more. I don't think you'll ever have to define it on a test, and it's something you'll come to understand slowly. So polarization, you've learned about it in chemistry and probably biology and maybe other places. It's just separation of charge within some object. So you can have a polar molecule that overall has 0 net charge, but you've got a water molecule with a positive charge on the protons and a negative charge on the electron, and overall it's neutral. So these are two different examples of polarization. Don't say the answer out loud. Give people a little time to figure it out. Which one of these is the conductor? Don't say it yet. Just think about it. Well, look at your paper, not my screen. So this is somebody has held a negative rod next to this material and polarized it. And somebody's held a negative rod next to this material and polarized it. So they're both polarized. Okay, which one is the conductor? B or C? C, yeah. So in C, the electrons have been repelled all the way from this side of the object to the other side of the object, causing a separation of charge. In this one, the electrons have been repelled all the way to the other side of the atom, causing a separation of charge. So let's see, the diagram on the right shows polarization. A conductor is polarized in diagram C, insulator in diagram B. And then the last question, if you were holding these rods and you brought them over next to this material or this material, what would you feel? Like just as you like say this is the negative rod, or bring it closer and closer to this material, what do I feel when it gets close, Cam? An attraction, yeah. Because once it starts to get polarized, then you've got these positive charges closer than the negative charges. So these are going to repel, but these are going to attract, and the ones attracting are closer. So the rod is attracted to the material. Coulomb's law we're going to skip for now. The homework is to, as I alluded to, do the John Travoltage FET simulation. On page 7 of your handout, it gives the address. You could just Google it. I'll show it to you in just a second. And there's some questions that go with it. Just do your best answering those. Don't keep yourself up late trying to get them right. It's okay. And then there's a balloon and static electricity one, and I'll show you what they look like. They're just the sound of them is fun. I'm not going to do a Kazouch because I don't want to spoil it for you. John Travoltage. It's HTML5, so it'll load fast. Very flexible elbow joint and a very flexible knee. All right, so it'll only go up to there and only to there. All right, so then there's also the FET balloon. And I don't know, did I already mess with this with you? Oh, I spoiled it. Oh well. And there's Brook Trout email. All right, it's almost time to go. 3 minutes. So again, homework is to do the John Travoltage and balloons and static electricity questions. It'll be pretty quick.